The demand for energy storage is constantly increasing. We rely on batteries to power everything from our smartphones to electric vehicles. Traditional lithium-ion batteries have limitations. They have limited lifespans and can pose safety concerns. Scientists are actively searching for alternative battery technologies to meet the growing energy demands. Aluminum-air batteries belong to a class of metal-air batteries, which are known for their high energy potential and innovative design. They utilize the oxidation of aluminum at the anode, a process that releases a significant amount of energy, and the reduction of oxygen at the cathode to generate electricity, creating a flow of electrons that can be harnessed for power. The anode consists of an aluminum metal plate, which is a readily available and cost-effective material, while the cathode is typically a porous carbon material that allows air to pass through, facilitating the necessary chemical reactions. During discharge, aluminum reacts with hydroxide ions from the electrolyte to form aluminum hydroxide, releasing electrons in the process. These electrons flow through an external circuit to the cathode, creating an electric current that can be used to power devices, where they combine with oxygen and water to produce hydroxide ions, completing the electrochemical cycle. The theoretical energy density of aluminum-air batteries is significantly higher than that of lithium-ion batteries, offering a promising alternative for energy storage. This high energy density makes them particularly attractive for applications where weight and size are critical factors, such as electric vehicles and portable electronic devices, potentially revolutionizing these industries. However, the practical energy density of aluminum-air batteries is often limited by the performance of the air electrode, which remains a significant challenge for researchers to overcome. The air electrode plays a crucial role in the performance of aluminum-air batteries. It is where oxygen from the air is reduced, completing the electrochemical circuit. However, this oxygen reduction reaction, or ORR, is sluggish, hindering the battery's overall efficiency. To overcome this limitation, researchers are exploring catalysts to accelerate the ORR at the air electrode. Manganese oxide or MnOx-based materials have shown promise as ORR catalysts due to their low cost, abundance and environmental friendliness. Graphene oxide, or GO, with its high surface area and excellent electrical conductivity, serves as an ideal support material for MnOx. The combination of NOx and GO creates a synergistic effect, enhancing the catalyst's activity and durability. The synthesis of MnGO catalysts involves a simple and scalable method. The first step is to prepare a GO solution by dispersing graphene oxide powder in deionized water. The GO solution undergoes ultrasonication to exfoliate the layers and create a uniform dispersion. Next, a manganese precursor, such as potassium permanganate, is added to the GO solution. The mixture is stirred vigorously to ensure uniform distribution of the manganese precursor on the GO surface. The amount of manganese precursor added determines the final loading of MnOx on the GO support. The mixture is then subjected to a hydrothermal treatment. This involves heating the mixture in a sealed autoclave at an elevated temperature. During this process, the manganese precursor is reduced and deposited on the GO surface, forming MnGO nanocomposites. Section 5. The power of ultrasound tuning catalyst properties. In this section, we delve into the fascinating world of ultrasound and its significant impact on catalyst properties. Ultrasound plays a crucial role in controlling the properties of MnGO catalysts during synthesis. It allows scientists to manipulate various parameters to achieve desired outcomes. By varying the ultrasonic amplitude, researchers can fine-tune the catalyst's morphology, particle size, and dispersion. This level of control is essential for optimizing the catalyst performance. Ultrasound generates cavitation bubbles in the liquid medium. These bubbles are tiny and powerful, playing a pivotal role in the synthesis process. These bubbles collapse, creating intense local heat and pressure. This phenomenon is crucial for altering the physical and chemical properties. This can influence the nucleation and growth of MnOx nanoparticles on the GO surface. The precise control over these conditions is what makes ultrasound so powerful in catalyst synthesis. Higher ultrasonic amplitudes generally lead to smaller air NOx particle sizes and a more uniform distribution of the GOs. This uniformity is key to enhancing. This is because the intense cavitation generated at higher amplitude promotes better mixing and mass transfer. Efficient mixing ensures that the reactants are evenly distributed. The smaller particle size and higher dispersion of monox nanoparticles result in a larger active surface area. This increased surface area is crucial for catalytic reactions. This is beneficial for catalytic activity as it provides more sight for the OA. Ultimately, the use of ultrasound in tuning catalyst properties leads to more efficient and effective catalysts. Section 6. Unveiling the structure characterization techniques. After synthesis, MEN-GO catalysts undergo thorough characterization to analyze their structure, composition, and properties. X-ray diffraction, or XRD, is used to determine the crystal structure and phase purity of the monox nanoparticles. Raman spectroscopy provides information about the vibrational modes of the materials which can be used to identify the presence of specific chemical bonds. X-ray photoelectron spectroscopy, or XPS, is employed to analyze the elemental composition and chemical states of the elements present in the catalyst. Field emission scanning electron microscopy, or FESM, and transmission electron microscopy, or TM, provide high-resolution images of the catalyst's morphology, revealing the size, shape, and distribution of the NOx nanoparticles on the GO support. Brunauer-Emmett-Teller, or BET, analysis is used to determine the specific surface area and pore size distribution of the catalyst. Section 7. Electrochemical testing, evaluating catalyst performance. The electrochemical performance of MEN-GO catalysts is evaluated using various advanced techniques to ensure accurate and reliable results. Cyclic voltammetry, or CV, is a common and widely used method to assess the catalyst activity toward the oxygen reduction reaction, or ORR. This technique provides valuable information about the electrochemical properties of the catalyst. In CV, the potential of the electrode is swept linearly with time, and the resulting current response is measured. This helps in understanding the redox behavior of the catalyst. The peak current density and the potential at which the peak occurs provide insights into the catalyst's activity. These parameters are crucial for determining the efficiency of the catalyst in the ORR process. Linear sweep voltammetry, or LSV, is another technique used to evaluate the catalyst's ORR activity. It complements the data obtained from CV by providing additional information on the electrochemical behavior. In LSV, the potential is swept linearly from a starting potential to an ending potential, and the current response is recorded. This method helps in identifying the onset potential and other key parameters. The onset potential, which is the potential at which the OR current starts to increase, is an important parameter that reflects the catalyst's activity. A lower onset potential indicates a more efficient catalyst. Chronoamperometry is a technique used to assess the catalyst's stability over time. By applying a constant potential and measuring the current, researchers can evaluate how the catalyst performs under prolonged operation. Section 8. Battery discharge performance, putting catalysts to the test. To evaluate the practical performance of MEN-GO catalysts in aluminum-air batteries, researchers conduct battery discharge tests. These tests involve assembling a complete aluminum-air battery using the synthesized MEN-GO catalyst as the air electrode material. The battery is discharged at a constant current density, and the voltage and discharge time are recorded. The discharge performance is analyzed to determine the battery's capacity, energy density, and power density. The capacity refers to the total amount of charge that the battery can deliver at a given discharge current density. The energy density represents the amount of energy stored per unit mass or volume of the battery. The power density is a measure of how quickly the battery can deliver energy. Section 9. Conclusion. A step towards efficient energy storage. The development of efficient and durable catalysts for the oxygen reduction reaction is crucial for advancing aluminum-air battery technology. MnGO catalysts have emerged as promising candidates due to their low cost, abundance, and excellent catalytic activity. The use of ultrasound during synthesis provides a facile way to control the catalyst's properties, such as particle size and dispersion, which significantly influence its performance. By optimizing the synthesis parameters, researchers can tailor the properties of MnGO catalysts to achieve enhanced ORR activity, leading to improved performance in aluminum-air batteries. Further research and development in this area hold great promise for realizing the full potential of aluminum-air batteries as a viable energy storage solution for a wide range of applications.